There are obviously lots of different types of solids, but pretty much the only ones you're going to need to worry about can be categorized in four different groups: prisms, cylinders, pyramids, and cones. And there's quite a bit of similarity between some of these that'll help you um, keep everything in track. So let's take a look at prisms first. So a prism is defined as a solid that has a base, and that gives it its name. So if the base is a triangle, it's a triangular prism. If the base is a square, it's a square prism. If the base is a rectangle, it's a rectangular prism. The base can be actually any polygon. So you could have a pentagonal prism or a hexagonal prism. And the prism has two identical bases, and the other faces on a prism are all rectangles. So a triangular prism has two triangular faces, which are the bases, and then three rectangles. A hexagonal prism would have two hexagons as the bases, and then six rectangles. In cross section, the prisms are always the same. So we'll start with a triangular prism, and the triangle can be any type of triangle that we've encountered. So let's start with a fairly straightforward one, which is a triangle that has it's a right triangle. It's supposed to be a right triangular prism. And let's give the lengths of the two legs as 3 and 4. And then we have the height of the prism. Now, the height of the prism is defined as the distance between the bases. So you don't have to think of height of the prism as something from top to bottom. It's defined in a specific way. It's the distance between the two bases. It doesn't matter how the prism is oriented. And in a way, this isn't too different from the way we use height in English. If you talk about a person having a height of 6 feet, their height doesn't change when they're lying down, right? We define the height of a person as the distance between top of the head and bottom of the feet. And same with a prism. It's the distance between the bases. So here we've got our three-dimensional solid, and the volume of a triangular prism is the same as the volume of any prism, which is the area of the base times the height. So the area of the base times the height. So let's give this prism a height of 10 units. So when we go to calculate the volume, we do need to be able to find the area of the base. And in this case, it's straightforward because it's a right triangle. But if it's not a right triangle, of course, you're going to need to know the height of the triangular base. All right? So we've got height being used in two different ways. You've got to make sure you keep them straight. The triangle itself has a height, which allows you to calculate its area. And the prism has a height, which is simply the distance between the two bases. So in this case, we've got a straightforward right triangle. The area of the base is 3 times 4 divided by 2. And then we're multiplying that by the height of the prism, 10. So we get 12 over 2, which is 6. 6 times 10 gives you 60. So this prism has a volume of 60 cubic units. So if the units are centimeters, it'd be 60 cubic centimeters. If the units were feet, it'd be 60 cubic feet. Now, the surface area, probably the trickiest part of surface area for any solid is just making sure that you actually accounted for all the surfaces. So when I do the surface area calculations, I like to sort of block it out in a template form first and write down what am I actually trying to find the surface area of. I am finding the area of two triangles, all right, the two bases, and then there's going to be one rectangular face for every side of the base. So if it's a triangular prism, you're going to have 3 rectangles, and so I've got 3 rectangles I need to calculate the area of. Now, the triangular bases are identical, but the rectangles are not. So I've got 2 triangles, and we've already just calculated the area of the triangle. It was 3 times 4 divided by 2. The 2's cancel quite nicely. But the 3 rectangles, well, one of them is going to be, let's say, the bottom of the prism, the way I've drawn it, which is 3 times 10. One of them is going to be the back side of the prism, the way I've drawn it, which is 4 times 10. And then one of them is the sort of face that we're actually looking at, but we don't know one of the dimensions because we haven't calculated the hypotenuse. Now in this case I've used a very simple right triangle, and you could hopefully by now spot it as a 3, 4, 5 right triangle, but you can use Pythagoras to find that hypotenuse as well. And you can now calculate the area of that face. It's 5 times 10. So when you add this all up, you get 12 plus 30 plus 40 plus 50, which all adds up to 132. And that'd be 132 square units. So again, if it's in centimeters, it'd be square centimeters. If it was in feet, it'd be square feet. Alright, so let's take a look at a different prism just to see how things work. This is going to be an example of a square prism. And a square prism means it has a square base. So we've got a square, and let's make the square of edge length 3. And then we have a height, which again is just the distance between the two bases. So if the height of this is 5, we have volume. And the volume calculation here is particularly easy because it is just simply 3 squared times 5, the area of the base times the height. So that's 9 times 5, which is 45. And the surface area, again, is pretty easy because each of the rectangular faces is actually identical. So we have 2 squares, right, the 2 bases, and we have 4 rectangles, but this time we can actually just do 4 times the area of one of the rectangles. So the squares are 3 squared, or 9. The rectangles are all 3 by 5, so 3 times 5. And here we end up with 2 times 9, which is 18, plus 12 times 5, which is 60. And we end up with a surface area of 78. So you can call it 78 square units. If no units are given, it's quite common in math just to write the surface area as 78. But of course, if it's again, if it's in centimeters, it'd be square centimeters. If it was in feet, it would be square feet. Now let's take a look at a cylinder. So in some sense, you can think of a cylinder as a type of prism. It's not technically a prism because the base is not a polygon. The base is a circle. And prisms have only flat surfaces, whereas obviously a cylinder has this curved surface. But in other respects, it's actually very, very similar, in particular, the volume. So let's do a little diagram of a cylinder here. The volume of a cylinder is simply the area of the base times the height. So in that respect, it's identical to a prism. And we know the area of the base in this case is pi r squared, and then multiply that by h. So we need to have the height h, and we need to know the radius of the circular base. So for this one, let's say the radius is 3 and the height is 5. If we want to calculate the volume, the area of the base is pi times 3 squared, and the height, multiply that by 5, and we get 9 times 5 is 45 pi. And remember, the best way to leave this is just as a multiple of pi, 45 pi. You could pull out a calculator and get a decimal approximation for that. Because pi is a little bigger than 3, you know this is going to be somewhere around 150. But that would just be an approximation, and it's perfectly fine to leave it as 45 pi. Now, for the surface area, it's a little different than a prism, but again, you want to make sure you keep track of all of the different surfaces. So we have 2 circular bases, so we're trying to find the area of 2 circles. That's a circle, not an O there. And the lateral surface, which is the curved part that wraps around the cylinder, is actually a rectangle. If you've ever cut the label off a can, you know that when it unwraps, it is a rectangle. And that rectangle has a height, obviously identical to the cylinder, and the length of that rectangle has got to be a long enough rectangle to wrap all the way around. So it has to have a length equal to the circumference of a circle, which is 2 pi r, or pi d. But normally we're given the radius, and we certainly need the radius to find the area of the circle, so it makes more sense to refer to it as 2 pi r. And so when we go to calculate the surface area, we've got all the information we need. we have 2 times pi r squared, r is 3 in this case, and then we have that one lateral surface, the one rectangle, so it's 2 times pi times the radius 3 times the height 5. And so again, leaving this as a multiple of pi, we have 2 times 9, which is 18 pi, and then we have 2 times 3 times 5, which is 30 pi, and add them up and you get 48 pi. And that really is the best way to leave that surface area. Okay, so let's take a look now at pyramids. So a pyramid is related to a prism in that it has a base that's a polygon. But instead of having rectangular faces, it has triangular faces, and instead of having two bases, it only has the one, with all of the triangular faces meeting in a single point called the apex of the pyramid. Now, that being said, there are actual similarities, though, and we're going to see the similarities when we go to calculate the volume. So it's helpful to have a half-decent diagram, and I'm going to draw a square pyramid here. And when I draw the square pyramid, I'm going to do it sort of in profile, and I'm going to try to locate the center of the square base by doing these extra little lines halfway along, and then I'm going to do a dotted line to represent the height of the pyramid. Then I'm going to connect each vertex with the apex and create this three-dimensional rendering of a pyramid. Now, the pyramid has a height. Let's say that in this case the height is 12. And if the base is a square, this is a square pyramid. So when we go to calculate the volume of a pyramid, the volume is the area of the base times the height divided by 3. So the area of the base times the height is the volume of a prism. The pyramid basically just means you're actually taking 1/3 of the volume of a prism with the same base and the same height, which is a really nice relationship. It's not all that intuitive, and you actually need calculus to prove that. But for now, just accept it as a nice fact. And it's a fact that you should keep in mind, because there will be some questions that might crop up involving the ratio between the volume of a pyramid and a prism that have the same base and the same height. So for instance, a pyramid that is inscribed in a prism. You could imagine this square pyramid inside or fitting inside a square prism. Same base, same height. How much of the volume is taken up by the prism? Well, 1/3 of the volume. All right, so that's important to keep in mind. So in this case, let's calculate the volume. The area of the base is very easy because it's just a square, 10 squared. The height is given as 12, and then we're dividing that by 3. So that's 100 times 4, which is 400. Now, once again, surface area, we've got to be a little bit careful to make sure we've actually accounted for all the surfaces. So what are we doing when we calculate the surface area of this pyramid? We have a single base, which in this case is a square, and then we have 4 identical triangular faces. Those triangular faces are not always going to be identical depending on what the base is. So for instance, if the base is a rectangle, you're going to have 2 pairs of identical triangular faces, and if the base was something else, you might not have all identical triangular faces. So the area of the square is straightforward. It's simply 10 by 10, so 10 squared. But what's the area of each triangular face? Well, you may think, okay, it's base times height over 2. But what's the height? It's not the same as the height of the pyramid. So the height of the pyramid is the distance from the apex to the middle of the base, the center of the base. Whereas the height we want now is the height of each triangle. And this is where having a nice diagram helps, because you can see that the height of the triangular faces is actually the hypotenuse of a right triangle, where the legs of that right triangle are the height of the pyramid, which is 12 in this case, and half the length of one of the dimensions of the base. So in this case, half of 10 is 5, and the height is 12. So you can use Pythagoras, or hopefully recognize that it's a Pythagorean triple, 5, 12, 13. And so this height that we're looking for is called 13. Now, to distinguish between these two heights, the height of the pyramid and the height of the triangular face, we give the height of the triangular face a different name. It's called the slant height. So the slant height of this pyramid is 13, and that means that the height of each triangular face is 13. The slant height obviously has to be bigger than the height of the pyramid. So let's work that into our formula here. The area of each triangle is going to be the base of the triangle, which is 10, times the height of the triangle, which is 13, divided by 2, and there are 4 of them. All right, 4 identical triangles. So this works out to 100 plus 260. And so the surface area of this pyramid is 360. All right, so let's take a look now at cones. And just as there was this nice relationship between cylinders and prisms, we can sort of think of a cylinder as a circular prism. We can also think of a cone as a circular pyramid. And the relationship in volume is exactly the same. So if we have a circular cone, again, let's have a nice little diagram. It's actually quite important. We have a height and a radius. So the volume is simply equal to the area of the base times the height divided by 3. So that looks exactly like the volume of a pyramid. And in this case, the area of the base is fairly easy as long as you're given the radius. So let's imagine that the radius for this one is 6. And the height is 8. Let's figure out the volume of this cone. So we have the area of the base is, well, it's a circle, so it's pi times the radius squared, so pi times 6 squared. The height is 8, and we divide that whole thing by 3. So we end up with 36 times 8, which is 288, divided by 12, which is 96, I believe. Or let's see, hold on. 36 divided by 3 is 12. 12 times 8 is 96. So we end up with a volume of 96 pi. Now, again, you could be asked a question about the relationship between the volume of a cone and the volume of a cylinder with the same base and the same height. So clearly the cylinder is 3 times the volume if they have the same base and the same height. Surface area. All right, for surface area, one thing to keep in mind is that all of these solids are known as closed solids. The most common cone that you're going to come across is like a filter, like for filling oil in your car, or some kind of cone for cooking, and these are open cones. But all of the solids that you're going to deal with for the most part are closed, which means you have to account for the circle on the bottom. So the surface area is the circle on the bottom, which is pi r squared. That's just the area of the circle on the bottom. The lateral surface has a nice compact formula. It's pi times the radius times s, where s is the slant height. So once again, we need to calculate the slant height. And the slant height, just like with the pyramid example, the slant height is the hypotenuse of a right triangle. In this case, I've again picked a Pythagorean triple. It's an example of a 3, 4, 5 Pythagorean triple. Just multiply each of those by 2, and you get 6, 8, 10. And if you didn't spot that, you could always use Pythagoras. So to calculate the surface area here, we have pi times the radius squared, so pi times 6 squared, plus pi times 6 times 10. And this comes out to 36 pi plus 60 pi, which is 96 pi. So it'd be 96 pi square units.